few quick notes about the nth term test and a few more things about the geometric series. The nth term test is a test for series divergence. That's it. So if you have a series, the test says if the terms don't converge and tend towards zero, then the series diverges. So if the terms are getting bigger, the series diverges. If the terms are approaching 3, the series diverges. If the terms aren't approaching 0, the series diverges. Now this is one directional. The converse is not true. Let's try an example. Does this series diverge or converge? We're going to try the nth term test for divergence, which just says this. Have that memorized. Here we go. As n approaches infinity, the terms, the a sub n terms, are 0.84 to the 1 power. Well, that gets smaller and smaller and smaller. That's equal to 0. Our conclusion, we can't make any conclusion. This tells us nothing about when the terms converge to 0. All it tells us is if they don't converge to 0, the series diverges. So the nth term test is inconclusive. We got nothing. So we don't have an answer to this series. Next example. Here we go. So the limit of the nth term as n approaches infinity is 4/3. So we say this is not equal to 0, and therefore, by the nth term test, the series diverges. All right, now a few things about geometric series with respect to the notation, expanded form, and the communication that's absolutely required when determining whether the series converges or diverges. Every one of these series will be identical, but we're going to change the notation. The lower index we're going to raise from 1 to 3. And then when we come down here, we're going to lower it from 3 down to 0. So how can we have equivalent series in every case? When the index goes up by 2, then in the expression, that variable has to go down by 2. N minus 1 becomes n minus 3. Similarly, if the index goes down by 3, then in the expression, it has to go up by 3. So for these geometric series, we can write them with an index of 1 or 0 or 3 or whatever we want. And sometimes people choose to do that, so the exponent here is just plain old n as opposed to n minus 1. But they're all the same, and we can show that by expanding. Starting with 1 or 3 or 0, when you expand these, you get the exact same set of terms. Let's look at an example. Often it helps to expand these, but let's just suppose we wanted to write it in the form of the first term times the common ratio to the n minus 1 power. When we expand it, we can see that that's our first term. So, first term, what are we multiplying by every time? To the n minus 1 power. And you can see what we're multiplying by is a negative 4/5. Negative 4/5. That's our common ratio. All right. In terms of the notation, we could also write it this way. We could start at 0 instead of 1. Remember, if this index goes down by 1, then by that letter n in the expression, it has to go up by 1. This accomplishes the same thing. Both of these expand to exactly this series. Converge or diverge, what's the communication that's required? Here we have a series. Is it geometric? If you expand it, you'll see that it is. When you expand it, we get that. And it's multiplied by 1/pi every time, so it's geometric. And that ratio is 1/pi. So first term times the ratio to the n minus 1. This generates this series. Notice these look different, but they're algebraically equivalent. This one here just happens to be standard form. All right, does it converge or diverge? To answer that question, you are going to have to say the following. Identify it as a geometric series, that's part 1. Part 2, don't just give this value, but you have to say what it is. It's the absolute value of the ratio. Its value, 1 over pi, is smaller than 1, and since it's smaller than 1, our series converges. Here's another quick example. This series is just that, and it's getting multiplied by this number every time. When that is 1, it's just that, and then it's that times itself, over and over again. And so we recognize this is a geometric series. The common ratio is what it gets multiplied by every time, which is 1.001. That's bigger than 1, therefore the series diverges. Remember, we can write this as a geometric series in standard form, where the first term is 1.001, and then the common ratio is 1.001, and it gets raised to the power of n minus 1. They're exactly the same. One last observation, beware of this formula for the sum of a converging geometric series. We derived it in period B5 as a1 over 1 minus r, but really you should think of this as first term, not necessarily a sub 1. If you're wondering, what do you mean? Well, look at this series. This series here starts at 3, and so if we expanded it, that would be 2/5 to the third plus 2/5 to the fourth, and it goes on and on and on. And if you go and use this formula and you say, well, this is a geometric series, the absolute value of the ratio is 2/5, which it is, that's smaller than 1, and therefore the series converges. And if you use the formula a1 over 1 minus r, you might mistakenly say 2/5 to the 1 power because you're thinking a sub 1. But really, you should think of this as first term. It's the first term over 1 minus r. So do that instead, and your work will look like this then. There's our series expanded a bit. It's geometric. The absolute value of r is 2/5, which is less than 1. Therefore, a series converges, and it converges to first term over 1 minus r. That's the formula. That's the way to think about it, so you don't make this mistake. And that was 8 1/25 over 1 minus r, which is 8 75ths, and I think that's it. Yep, that's it. Have a nice weekend.